What if you could discharge a firearm around a concrete wall without exposing the operator? In 1944, German engineers attempted to rewrite the laws of ballistics. They abandoned the straight line, forging a weapon with a radically bent barrel. Designated the Krummlauf, media often romanticizes it as a secret superweapon. But raw physics tells a drastically different story. Inside this curved steel tube lies an intense mechanical mystery. A violent clash of extreme kinetic friction, explosive gas pressure vents, and catastrophic barrel erosion. To understand why bending a gun barrel pushes metallurgy to its absolute breaking point, we must look inside. By late 1944, infantry units were trapped in grueling urban warfare. Engaging targets around a blind corner meant immediate neutralization from concealed marksmen. Peeking out just 3 inches invited ballistic trauma. Simultaneously, mechanized tank crews faced a critical vulnerability. Hostile forces could easily approach dead zones to attach magnetic anti-tank charges. To solve this tactical nightmare, engineers commandeered Germany's primary assault rifle, the Sturmgewehr 44. They clamped a heavily modified, curved barrel extension onto the muzzle. Paired with a prismatic mirror periscope, this configuration allowed an operator to remain behind solid concrete cover while discharging the weapon around 30-degree obstacles. On the drafting table, it looked like tactical perfection. In reality, it triggered a war against fluid dynamics. The complete Krummlauf system relied on 2 critical components, a bent barrel extension, and a mirror periscope. The standard infantry version utilized a 30-degree curved attachment. Conversely, engineers designed 45 and 90-degree variants specifically for mechanized tank crews operating in confined armored spaces. The optical system was ingeniously simple. The operator looked through a dual mirror periscope mounted above the receiver. Ambient light reflected off a primary mirror angled at 45 degrees, traveling downward to a secondary mirror aligned with the operator's eye line. This allowed precise target acquisition around structural cover without raising the helmet above the barricade. But optical reflection is easy. Guiding a supersonic projectile through a curved steel pipe requires an extraordinary manipulation of ballistic forces. Let us examine the raw thermodynamic physics. When the cartridge detonates, expanding propellant gas pressurizes the barrel to approximately 50,000 pounds per square inch. The projectile accelerates to over 2,200 feet per second. But as this supersonic bullet impacts the curved internal wall, it generates immense kinetic friction. The bullet slows down abruptly, but the superheated gas behind it continues expanding violently. Without modifications, this trapped high-pressure wave would rip the attachment off the muzzle. To prevent catastrophic blowout, engineers drilled gas relief vents near the base of the curve. As the bullet enters the bend, these ports bleed off the rapidly expanding gas into the atmosphere. This dumps the pressure and stabilizes internal dynamics. However, this drastically reduced kinetic energy. Projectile velocity plummeted from 2,200 feet per second down to a mere 980 feet per second. This is where Newtonian physics exacted its brutal revenge. When a full metal jacket projectile impacts the curved inner wall at supersonic speeds, centrifugal force generates massive radial acceleration. The bullet is physically crushed against the outer radius of the steel curve. Instead of sliding smoothly through the bend, the soft lead core and copper jacket violently deform under immense stress. The projectile essentially shatters before leaving the barrel. It exits the muzzle not as a unified solid projectile, but as a chaotic spray of jagged metal fragments. It effectively transformed a precision assault rifle into an unpredictable short-range shotgun. Furthermore, extreme friction literally melted away the internal rifling. A standard 30-degree barrel lasted barely 800 rounds before failing. The extreme 45-degree tank attachment suffered catastrophic internal erosion after a mere 300 shots. Despite these overwhelming mechanical flaws, the military rushed the Krummlauf into emergency production for specialized defensive roles. The 90-degree P variant was rigidly mounted onto armored vehicle roof hatches. Secured on a rotating ball joint, it allowed crews to sweep incoming threats away from the hull without exposing themselves to hostile fire. In a static defensive posture, it functioned adequately. However, for mobile infantry, the system proved disastrously unwieldy. The bulky steel extension and heavy optics drastically shifted the weapon's center of gravity forward. This threw off the ergonomic balance, making standard offhand aiming exhausting and nearly impossible. Combined with the abysmally short barrel lifespan and the erratic bullet trajectory, the system was a logistical nightmare. Less than 500 functional units were fielded before the conflict concluded. The Krummlauf remains a fascinating mechanical paradox. It was an incredibly creative conceptual solution to the brutal realities of urban combat. Yet, it was sabotaged by the unforgiving laws of kinetic physics. Forcing a high-velocity projectile to negotiate a curved steel tube could not change the basic scientific fact: physical objects in motion desperately want to travel in a straight line. However, the core tactical concept never died. Decades later, modern defense engineers realized a fundamental truth. Instead of fighting ballistic physics by bending the barrel, they should bend the weapon frame itself. This led to modern platforms like the corner-shot system. By utilizing specialized hinged chassis designs and digital high-resolution cameras, modern operators achieve exactly what engineers attempted in 1944 using rudimentary bent steel and mirrors. The Krummlauf stands as one of history's most bizarre military experiments. It proved definitively that while engineering ingenuity can push mechanical boundaries, raw physics and material science will always have the final say. Which failed prototype or misunderstood military invention should we dissect next? Let us know in the comments section below. Make sure to subscribe to Arsenal Anatomy, and we will see you inside the next three-dimensional mechanical breakdown.